So this question is a very common type of cantilever beam analysis, and what we have here is a cantilever beam with a hollow circular cross section, and we get the diameters, we get the thickness, and we have there the length of the beam, and we need to determine the maximum bending stress. So we're going to use a chunk of this formula that I'll write out. So the I in the formula, it represents the second moment of area of a tube, and the formula for that is pi multiplied by d to the power of 4, and that's the outer diameter, so d2 to the power of 4 minus d1 for the inner diameter to the power of 4 again, and all divided by 64. So we're calculating here the second moment of area, and whilst I'm going through, I'll just talk you through what that means as well. So the second moment of area is representing the beam's resistance to bending in this case. So 0.12 to the power of 4 and all over 64. So what we get here for our second moment of area is 1.467 times 10 to the negative 5. And our unit is meters to the 4th power. Now I really hate to break the flow of the video, but if you could give the video a thumbs up and subscribe to the channel if you haven't done so already, that would help massively. It does help the channel's discoverability, and hence more students get access to the content. So we're calculating now our maximum bending moment at the fixed end, and what that is, it's just going to be our weight or our force times the length, and it was 4 kilonewtons, so we have 4 kilonewtons, so 4 times 10 to the power of 3, and the length that we had was 1.8 meters, so this will be 7.2 kilonewton meters. So this here is what represents our maximum bending moment at the fixed end. So the M in the formula, it represents our maximum bending moment. And if there were other point loads, then we would just sum them all up to get the total. So our next calculation is just going to be the distance to outer fiber of the tube. And all that is the y, so it's representing the y that's in the formula, and the y itself, it represents the distance from the neutral axis. So this is just going to be our outer diameter, so d2, and just divide that by 2. So what we have is 0.15 divided by 2. So this is 0.075 meters. So that takes care of the y in the formula. So our next step is to find the maximum bending stress. So this was the formula that we started off with, and we're going to just rearrange it using what we have to find the maximum bending stress. Now, the other two variables in the formula that we have not yet heard of or mentioned yet is the E, which represents Young's modulus, or the modulus of elasticity of the beam's material, but we're not going to use that in this question because we didn't get that value. And the other variable is the R, which is representing the radius of curvature of the neutral layer of the beam due to the bending moment. But again, we didn't get that, so we won't use it in this question. So let's now calculate the maximum bending stress because we have everything that we need. So this is our 7,200 or 7.2 times 10 to the 3 for the maximum bending moment that we calculated, multiplied by our value that we got for y, and all divided by what we got for the second moment of area. So that leaves us now with a final value of 3.681 times 10 to the power of 7, and that's newtons per meter square. Now we could just rewrite this as 36.8 megapascals, and that would be much better. So hope you have found this video helpful, and until next time, I will see you in the next video.